A sprinter crosses the finish line. A high-speed train blurs past. A digital stock trade executes. Today, we measure success in milliseconds. For thousands of years, humans had to organize agriculture, navigate oceans, and survive the seasons without a single clock. They relied entirely on nature. Early civilizations looked up. They watched the Earth rotate and the moon cycle through its phases. These predictable movements allowed them to divide existence into measurable blocks we call days and months. Finding those repeating patterns was the only way to impose order on a chaotic world. The earliest attempt to track time during the day was the sundial. By placing a stationary stick, called a gnomon, on a flat surface, people could watch its shadow move as the sun tracked across the sky, dividing daylight into hours. Centuries later, this concept reached its peak in Jaipur, India, at the Jantar Mantar Observatory. The centerpiece here is the Samrat Yantra. It stands 27 meters tall. Because of that massive height, its shadow moves exactly 1 millimeter per second. Observers could read the time with an accuracy of 2 seconds, using nothing but stone and sunlight. But when the sun sets, sundials become useless. To measure time at night, ancient engineers designed the hourglass, which relied on a measured flow of sand, and the clepsydra, or water clock, which tracked the steady, regulated drip of liquid from one vessel to another. These methods had limits. Sundials fail in the rain. Water freezes. Sand requires a human to flip the glass every hour. To truly master time, humanity needed a weatherproof machine that could sustain its own rhythm. In the late 1500s, a young student named Galileo Galilei watched a chandelier swinging from a cathedral ceiling. He realized that mechanical objects could create their own predictable, repeating rhythm. In physics, we call this periodicity. This is a simple pendulum. You have a weight at the bottom called the bob. When it hangs straight down, it sits at its resting center, or the mean position. As it swings, it reaches its furthest points on either side, the extreme positions. The distance it travels from the center to an extreme position is its amplitude. Galileo discovered that as long as the string length stays the same, the time it takes the bob to complete one full back and forth swing, its time period stays constant. Even as friction slows the pendulum and the amplitude shrinks, that time period remains the same. It is easy to assume a heavier weight would swing faster, but the mass of the bob has zero effect on the speed of the swing. A heavy iron anvil and a light wooden bead on identical strings will swing in perfect simultaneous rhythm. This mathematical relationship means that any pendulum with a string length of exactly 1 meter will consistently take about 2 seconds to complete one full oscillation. By harnessing a law of physics that ignored clouds, rain, and temperature, the invention of the pendulum clock turned timekeeping into a precise mechanical process. Yet, mechanical gears still grind. Even the best pendulum clocks experience friction and lose a few seconds every day. To achieve true precision, engineers had to look smaller. They found the answer in quartz crystals. When a piece of quartz is zapped with electricity, it vibrates. It oscillates millions of times per second with microscopic regularity. Then came the atomic clock. Instead of vibrating crystals, these machines measure the natural resonance of individual atoms. This gave us the exact definition of the SI unit of time, the standard second. Shifting our focus from giant planetary shadows down to invisible atomic vibrations established a standard of time that loses only 1 second every million years, the precise baseline needed to measure the physical world. Now that we have mastery over the second, we can calculate motion. In physics, motion is simply an object's change in position over time. This brings us to a foundational formula. Speed equals total distance divided by total time. If a bus travels a total distance of 150 kilometers and the journey takes 3 hours, we divide 150 by 3. The resulting speed is 50 kilometers per hour. While kilometers per hour is common, scientists use meters per second. You convert it by multiplying by 5/18. In this case, our bus is moving at 13.8 meters per second. You interact with these concepts every time you sit in a car. The odometer tracks your total distance traveled. Right next to it, the speedometer tracks your instantaneous speed, exactly how fast you are going at this exact second. That number constantly changes, which is why it's usually different from the average speed of your whole trip. These abstract equations of physics are physically built into our vehicles, making the invisible math of motion visible. To understand how things move, scientists translate speed data into visual stories. This is a distance-time coordinate graph. The horizontal x-axis tracks time in seconds, and the vertical y-axis tracks distance in meters. If an object covers equal distances in equal amounts of time, meaning its speed never changes, it creates a perfectly straight diagonal line on the graph. This is called uniform linear motion. But if the line curves sharply upward, we are looking at non-uniform motion. A common mistake is thinking a curved line means the physical object is turning. On this graph, a curve only means the speed is changing. The object is accelerating. We started by watching shadows creep across stone steps in ancient India, trying to catch a glimpse of the hour. Dividing time into these perfect microscopic slices, from dripping water to vibrating atoms, is what allows us to calculate speed, plot distances, and accurately predict how objects move through the world.